This sort of processes are constantly happening in our universe, and if we can train our detectors to be sensitive to high energy gamma rays, we can learn a lot about these processes. So in terms of, just to get into a little more detail about particle acceleration, one source that I like to talk about is a supernova explosion. This is basically the, sort of the life cycle of a star, massive star. I mean, our sun, for example, in a few billion years is going to turn into a red giant. It's going to burn up all its fuel. What you end up with is a very compact core. This is something which can, it's basically you're left with a compact neutron star, and then there's nothing left to burn, and then all the material comes in. It's pretty much like a train wreck, a train crashing into a wall. It's just, you just have a tremendous explosion. Matter is blown away, a cataclysmic event, shock explosion, sort of stochastic shock acceleration. And the amount of sort of material being blown away at extremely high speeds. Enrico Fermi was an Italian-American physicist. He worked this out, paper and pencil. He was able to show in his calculation how much energy do you gain in shock processes such as this. What you need is basically a shock front, and you need magnetic fields, which exist in these sources, to accelerate charged particles like protons to cosmic ray energies over time. If you want to visualize this, you can think of this in this analogy of sports that I brought up. It's basically, it's like a ping pong paddle. It's like you're between, these particles are going back and forth, back and forth, back and forth between these shocks and magnetic fields, and as a result, it is getting accelerated, pretty much like when you play ping pong. It's just a similar process. It's just an extrapolation, sort of an idea. Okay, but this is, in events like this, a supernova explosion is really tremendous because the abrupt release of energy is comparable to the total energy output of our sun over its entire lifetime. And all of this is happening in a second, okay, in a few seconds. So it's a pretty tremendous process. And in fact, supernova, actual images of supernova have been well measured by other instruments, not by gamma ray experiments, but by other telescopes, radio telescopes, the Hubble Space Telescope. Beautiful images with visible light, and you can see here, these are some of the famous ones. These are some of my favorites. This one here is particularly interesting. This is called the Crab supernova remnant. It was named because of its crab-like, sort of structure, I guess, spidery structure. But this one here is, just to put a scale to it, is about 6 light years across. But this is a Hubble Space Telescope image, and all this blue that you see is basically electrons that are accelerated to extremely high energies in magnetic fields. The crab particularly is very interesting because this was a supernova explosion that happened about 1,000 years ago. It was in 1054 AD. The Chinese have records, so historical records of the Crab supernova explosion going off, because for something like this tremendous, you would actually see it with your naked eye in the night sky. And this one actually is interesting because you go back to the records of the Anasazi Indians in Arizona, mysterious people. You go back to their caves, there are these drawings here which show the crescent moon and the star here. If you just go back and historians look at the shape of the crescent moon, the position of the star relative to the moon, you could work out. I mean, some people think that this was probably the Crab supernova remnant being recorded by people, their naked eye. I mean, it would have been about 5 times as bright as the Venus in the night sky. So you would actually see it. It was a pretty powerful explosion. So for something like the Crab, what happens is you basically have a system, and so here is a little bit of detail on how physicists understand the model of what's going on in the Crab pulsar. You're left with, in an explosion after all the material is burnt away and the shock wave is swept away, you're left with a very compact object, what we call a neutron star now. And in this process, you have a very strong magnetic fields zooming out in both directions, and in those magnetic fields you have particles, charged large particles that are accelerated. And as a result, you see this, you have some numbers here. You can think of this as electric potential difference of quadrillions of volts. It's about 30 million times what you see in lightning. There's just tremendous amounts of energy that's being produced. And in fact, what you see here is, again, the same movie here. You see basically these two beams of light, pretty much like a lighthouse, and that the pulsar is spinning, and you have these beams of radiation, lighthouse, that are coming out. And we are lucky that the beams of light intercept Earth, and in the process we measure them. And every time, it's just like in a lighthouse beam, every time it turns around, the crab happens to turn out about 30 times per second. And you can measure the pulsations just by intercepting the beams of light. Okay, and as it's actually slowing down. As it's slowing down, it's losing energy, and that energy is being transferred in terms of radiation that you see across the electromagnetic spectrum. What is a neutron star? I mean, that's a very interesting topic by itself. Without getting into too much details, again, standard model of physics. You can think of what is inside your nucleus. You have a neutron and a proton.